by a solenoid actuator, the peak force that comes out of it, without regard to time, is the strength. All the rest of the definitions are truly physics. So that's one of the great things about this field, is it makes your physics real. So if you want to talk about work, work only occurs if this force drags something, a load, through a distance against gravity. So interestingly, when you guys go running, there's no Newtonian work. Because there is no, the muscles are not moving, it's all vertical. And then power, of course, as we said last time, it's the rate of doing work, the product of force times velocity. So it's all very much physics. And that was an email question from somebody yesterday. That's my answer so far. One other thing before we actually start on, I'm kind of excited about today's lecture because it is a big and important lecture. But before we do that, studying. Now is about the time when you start to fall behind, second week. I used to have a friend who said, what did he say? I was saying something about how hard the quarter system is. So I think it's great. And I said, what? He says, yeah, you're falling behind right away, so there's lots of time to catch up. Sort of an extreme optimism. I would say this is just cognitive science. I can't tell you how to study you personally because you're each you and have your own cognitive styles. But what science would show is that within 1 to 2 days after exposure to initial information, looking at it again is tremendously useful. And what everyone overdoes is they think they've got to learn the whole thing. No. Just open it up and kind of go through each slide. For instance, I got a text from my boyfriend on this slide, and I have no idea what he was talking about. Circle that, put a question mark on it, and realize you're probably going to come see me in office hour or look at it in detail on the weekend. So you're really getting the big picture. And you suddenly look at 5 slides in a row and go, these are all about how glycogen breaks down. And so you just make a little bracket and go, glycogen breaks down. So it's really the big picture. That's the hardest part to build, is the overview. And that doesn't need to take more than 20 minutes. Then, say at the end of the week, on the weekend, or in that empty Thursday afternoon slot that you have for reasons you don't understand, at some point you need to spend another kind of 45 minutes to an hour going through the details of each slide. That's a great time to use your review questions. So you look at the lecture and then you start to look at the review questions and see if you can answer them. If you can't, then you have to go back and dig out where in the lecture is the answer to that review question. That make sense? That's as much as I can tell you from the standpoint of what cognitive science would tell you to do. Whether you do that naked or where, so that's all your business. So today we're actually, I guess I'm excited because last time we were talking about ATP, and the only ATP regeneration systems we talked about were one enzyme each, creatine phosphokinase catalyzing creatine phosphate into ATP, and adenylate kinase. So these were really simple systems. Today is our first true metabolic pathway where there's some interesting features. There's choice at the beginning, there's choice at the end, there's choice in substrate, there's choice in product, and there is regulatory control by allostasis, by hormones, and so we're actually getting into some depth. So if glycolysis is the breaking down of glucose in the cytosol, this is often called anaerobic glycolysis. Again, it's a poor term. The term is at least 100 years old. Let's be more sophisticated. Incomplete glycolysis or cytosolic glycolysis. I promised to show you, I think you're familiar with what a glucose looks like. I promised to show you the body's starch, animal starch, which is glycogen. It's a true polysaccharide, meaning a chain of sugars. Thousands of glucose molecules are connected through a glycosyl bond. Okay? There is a central protein core upon which this elaborates, and that central protein is called glycogenin, the generator or seed of glycogen. Okay? Let's see, what other things are here? There are branches in this, so notice In fact, you're going to see this is important because you need two different enzymes to break this down. By far the most common enzyme is that glycogen phosphorylase that we talked about last time, and it snips one of these off and slaps a phosphate on it. When we get to these branch points, it's a different kind of a bond, and so you need a different enzyme to debranch it. And so that's the rarer function, but there is a second enzyme called debranching enzyme that's going to pull this apart. What else? A final point is, so let's see. You guys ever have sugar on your in your kitchen counter for your tea or coffee? You know how it turns into a block if you're not constantly disturbing it? Because it's hydrophilic. It's a glucose polar molecule. If you have a big polysaccharide, it sucks water out of the air. It is true, this is a starch. Oatmeal would be a good equivalent polysaccharide. Oatmeal is a big starchy substance. Notice how when you cook your oatmeal, you get kind of a gel. It gets kind of gooey. It's important to realize that every 1 gram of stuff is not stored in your cells as a powder because your cells are all wet. And so it's interesting, there's almost 3 grams of water associated with each 1 gram of glycogen. And you'll see that becomes important later because this is a secret source of water. As you use up your glycogen, you're also automatically releasing free water in the body.
Is that like the water weight? Is that the water weight?
That's part of water weight, yes. Part of it. I don't know. Okay, so there's glucose. I think you know about glucose. So there's a few highlights of glucose. Remember, your brain functions exclusively on glucose. Yes, it can use ketone bodies, but there's an adaptation range of doing that, and you're pretty miserable for a day or two. Our country is currently experiencing an epidemic of hyperglycemia among adults. The disease of chronic hyperglycemia is called diabetes. There's 2 kinds. This is not type 1, where the child loses the ability to generate insulin. This is not an epidemic. It's going along at the same rate it always has. The epidemic is this resistance to one's own insulin happening at the tissue level. That's type 2 diabetes, and as I've mentioned to several of you in office hour, this is as much a problem with underactivity as it is with overfeeding. Physical activity, I mean, just from the easiest point of view, the major place that glucose goes in, if you eat a bunch of carbohydrates and sugar, the main way it gets out of your bloodstream is to drain into the skeletal muscle. The easiest way to do that is if this glycogen granule has been chewed up by your day's activity and you need to rebuild it, it creates a huge drain for emptying the bloodstream of glucose. So if we are no longer being physically active, the same food load becomes stimulating the disease. So go out and chew up your glycogens on a regular basis. Hypoglycemia is, as I mentioned before, it's really quite rare at rest. What's interesting is if people are working hard, they'll blow through their glycogen in a fairly short period of time. Their muscles will start to suck from the bloodstream at a much greater rate. And so it's almost routine for someone who's exercising hard for 2 hours to become hypoglycemic if they don't take steps to prevent it. Kind of interesting. Someone was talking about we were talking about the various GLUT receptors. As I mentioned, there's a whole bunch of them, so there's at least 5. GLUT1 is our insulin independent, and so there's one. Neurons. Neurons don't need insulin because it's so important. Resting glucose uptake is often not dependent. I call this one the trickle charger, the drip charger. And then we have several. GLUT4 is your one that is the most insulin sensitive. Liver should be on here. Oh, is liver? There we go. Liver has its own high Km taker-upper of glucose. That makes sense. Insulin is the main driver of glucose out of the bloodstream after a meal. This word means after a meal, postprandial, after eating. And the primary place that glucose is supposed to go is in the skeletal muscle, unless it's already stuffed. Is this all okay? Just big pictures. So glycolysis is the breakdown of the glycose. There's about 10 enzymes. Each one has a specific, each step is a specific. This is all cytosolic. This is outside the mitochondria. The word for the anaerobic came up because most of the oxygen we consume is actually affiliated with ATP synthase on the inner membrane of the mitochondria, and so most human oxygen consumption is a mitochondrial phenomenon. So these steps can occur without oxygen. They also can occur with oxygen. They just don't care about oxygen. And since most humans are never hypoxic, all our tissues are usually saturated in oxygen, this word almost becomes useless. That's why I want you to throw it away, because you're all making lactate right now, and none of you are hypoxic. There's something wrong. That word is making you think we're yeast. That's most of what needed to be said. So we'll talk a little bit about control. So you have two sources. What I said, there's sort of almost like two sources of substrate for this, and there's two products at the end. So it actually becomes cool in the sense that there's decision trees, and in understanding your biochemistry, you actually start to use your brain and think, well, why is this set up this way? So the muscle can take from the blood glucose. We saw in an example at the beginning of the course that the total blood glucose is relatively small. It is the blood glucose in the strictest sense is meant for the brain. Hands off, this is for the brain. Butt muscle certainly can draw from the bloodstream and will, especially when it runs out of glycogen. Glycogen, oh, by the way, let's see. The glycogen comes in two places. There's glycogen in the liver, and that glycogen is really dropped into the blood. So in many ways you could say liver glycogen is for the blood, mostly for maintaining your brain function. Does that make sense? You'll see in a moment, muscle glycogen, muscles can't export glucose. You can't cut a glycogen, get a free glucose, and get it back out of the cell. Muscle lacks the reverse enzyme to hexokinase, which I think you would call glucose phosphorylase. It doesn't have that. The liver does. So the liver is the mother organ that can share with everybody. The muscle is an extraordinarily selfish little child. Mine, glucose, mine. So the glycogen of the muscle is for the muscle. We saw before that the breakdown, whether it's liver or muscle, breakdown of glycogen is regulated by epinephrine and calcium. Oh, let's plug this in to make it work. So here's an overview, and I like this because this is going to, I think this is going to give us our two different substrate sources. The substrate's always glucose. It's where you're getting it. So this is the boundary of the muscle cell. This is a capillary running nearby. Here is free glucose in the bloodstream. And so here's our typical, this is how it's taught in most classes, how this all works. And it's true for other cells, but for muscle it's really quite different. So glucose can come across the transporter on the membrane. Hexokinase, the thing that adds phosphates to a hexo, a 6-carbon group, takes an ATP, this should be inside the cell of course, and shifts the high energy phosphate onto the glucose at the 6th position, and this is now trapped in the cell. Notice that glucose phosphatase I was talking about, that only exists in exporting tissues like the liver. Muscle doesn't have this. Okay? Then the other source for muscle is the stored glycogen. Right? And the liver will tend to use its stored glycogen to drop it back into the bloodstream for the brain. It's again, the supportive organ is the liver. Muscle's glycogen is for it. It's highly selfish. Notice when you first break, we talked about glycogen phosphorylase last time, when you first break off a single glycosyl group, it comes out as glucose, 1, phosphate, different than the 6. I find that one very helpful because it helps me remember two things. Between the two different sources of glucose, which is the muscle going to use first? Its own glycogen. It's going to prefer its own glycogen because it's richer, it's right there, it's already in the cell, it's already been phosphated, for heaven's sake, so it's ready to go. The other thing that helps me remember, glucose is number 1. Yeah, that's good. Also, 1 means selfish, and so it's like this glucose is not available for export in a muscle cell. A liver cell can do it, but this is going to be fated to stay inside a muscle cell if it's a muscle cell. Now, because all of the enzymes of glycolytic pathway are set up to handle glucose 6-phosphate, you immediately isomerize this phosphate from the 1 position to the 6 position. So what would we call that enzyme? Isomerase. Glucose isomerase. Is this all okay? Okay. So notice we have 2 sources, glycogen and glucose. G1P, we're number 1, and then G6P. Then at the bottom, your typical product at rest, pyruvate. Notice you have a second product option, lactate. And when we get to the end of the lecture, we'll try to talk about what determines which of these is the predominant final product. And I'll give you a little foreshadowing right now. It hugely depends on how active the mitochondria is. If you're making 100 pyruvate per second and the mitochondria is accepting 100 pyruvate, there's no lactate production, or very little. If, on the other hand, you just started exercise and you're producing 1,000 pyruvate, you're working at 10 max, you're producing 1,000 pyruvate, and the mitochondria is still back at 100, well, goodness me, you're going to make quite a bit of lactate until the mitochondria gets sped up. Is that okay? As a quick and dirty picture. So let's look a little closer at glycogen stores. Here is, in a kind of average-sized human, if you were to add up the total grams, notice there's more total in the muscle, but it's distributed all through the body. The highest concentration of glycogen is in the liver. A lot of hunter-gatherer people will purposely eat the liver if they're having trouble getting to carbohydrate. Eskimo is a classic Inuit Eskimo. They love the liver because it's really hard to get veggies in the Arctic. And so, right, there's not a lot of carbohydrate in their diet. And so in order to keep their glycogen levels up, they will eat the liver of the polar bear or whatever they've killed. Let's see, so that gives you a good sense. Also, let's see, if we add these up, we get about 400 grams, which is about half a kilo. You can double that with training. We'll talk about training adaptation. I think we already did say the glycogen stores will expand. So you can get up to a kilo of glycogen. And then remember, that's 3 kilos of water, which is like 6 pounds of water. So when you're fully glycogen replete, you're a juicy puppy. And that water does become available as you use the glycogen up. What else? Oh, this shows you the breakdown process that the glycogen phosphorylase, which we've already talked about, will cut these. You get G1P as your initial production. When you get to the end of one of these chains, you're faced with this branch point, and that's what debranching enzyme does, is cuts that off. Notice once you cut off that tail or branch point, then you can just go through. So phosphorylase is by far the most active of the 2 enzymes, but you do need debranching enzyme. In fact, I think there's a glycogen storage disease where the person has a mutated form of debranching, and so they can't break down their glycogen all the way. They get stuck at that step, the debranching step. That's it. Okay. Remember that this process of glycogen breakdown is primarily, it certainly started up by the hormones, the catecholamines, epinephrine and norepinephrine. And we saw that through protein kinase, which is along this cascade, we get a phosphorylation of the, this is hard to say, of the glycogen phosphorylase kinase. So that's an enzyme that kinases, adds a phosphate to the phosphorylase. Am I doing that right? And so notice, so this is really a regulatory enzyme that turns this on and off. So the phosphorylase's only job is to cut glycogen. And it's not a deeply intelligent molecule, if you want to put it that way. Most of the regulation hits protein kinase. And I think we're going to look at that in a moment. So here's a detailed view. So what we said last time is, if you phosphorylate phosphorylase kinase, it speeds up. It becomes more active in activating phosphorylase. And then we said there were additional allosteric activators of both the regulatory protein and the actual enzyme itself that cleaves glycogen. And those regulators are calcium and low energy charge. So here's the deep and dirty details that I really don't want to know. But if you were to look closely at the regulatory molecule, phosphorylase kinase, you would have 1, 2, 3, 4 Greek-named subunits. And notice here's your phosphorylation by protein kinase. So this is phosphorylating the regulatory enzyme. It's got 2 phosphates, and now it goes fast. You can get a second level of activation if you had calcium, 2-phosphorylase kinase. So this thing is covalently regulated and allosterically regulated. Make sense? So you've got sort of an intermediate step, which would probably occur from hormone activity alone, since this is driven by protein kinase. So if you're just worried about your exam, or terribly frightened, you're in a fender bender, in an auto accident. I used to remember in the ER, you get people your age who are perfectly healthy. Coming in, they've been in something that scared the crap out of them without actually injuring them. And I would get their blood because you had to for the rest of the evaluation. And they come back with a blood sugar of 160. It took me a while. I said, "Oh, you got that?" And then it finally sank in. No, they were scared shitless. And so they had this epinephrine-based increase in the breakdown of glycogen in their liver. Then if you're actually doing true work, calcium and low energy state will come in and further increase the Yes?
Does that mean like being stressed chronically leads to?
Oh, does being stressed chronically lead to diabetes? Not directly in the way you're thinking, not biochemically. I'm not saying being stressed is a good idea, but the primary way that stress, you have to take my class in the spring, EXP 117, the primary way that stress messes up health is not so much from neurochemical imbalance, which I know all your other professors are teaching you that, and you should ask them to bring the controlled prospective data that shows that can happen in extreme cases. But what usually happens when you're stressed is you skip a workout, you light up a cigarette, you go find yourself a pie. So behavior is actually the most common way that stress messes up your health. Stress causes people to indulge in behaviors that are suboptimal, to be quite honest. It's a very advanced question and a very advanced answer. So, glycolysis, let's see. I like this. Look, we have contraction and its important role. But so here's glucose coming in. Oh, we're going to do an overview of glycolysis. I get it. Here's glucose coming in. We could also have glucose breaking down from glycogen. There should be a G1P in here somewhere. Once the glucose is in, it is trapped in the cell by phosphorylation, by hexokinase. Everyone in the world, there's a fun little point here to make. Everyone in the biochemistry world has taught you that this is a classic example of product inhibition. If you've already taken plenty of glucose from the bloodstream, we now will shut her down. Can you see now that you realize there's a second source what this is actually doing? This is telling you, keep your bloody mitts off the blood glucose as long as you have a sufficient supply of G6P from the glycogen. It's not a direct, I mean it is a direct feedback inhibition, but what it's actually functioning to do is cause the muscle cell to favor its own stores of glycogen over the blood glucose until such time as it's run out of glycogen. Does everyone see that? This is one of these sort of choice points that is biochemically set up. Then we're going to go in a moment through the 10 enzyme steps that lead down to pyruvate. And then as this shows here, pyruvate can directly enter the mitochondria, or pyruvate can be shifted over to lactate, and we'll consider that coming right up. So what does glycolysis do for us? I think starting down here, the most important thing about glycolysis is it's a preparatory step. It gets a 6-carbon molecule that is completely unwieldy down into 2 3-carbon molecules that can be decarboxylated as they enter the mitochondria, and then you have 2 acetyl-CoAs. So it's a prep step, if you want to put it that way. There's several other advantages to this prep step. It actually can, in a very quick way, because it's only 10 enzymes, regenerate ATP in the cytosol. So if you just started work and your mitochondria is not on board yet, you can get a rapid source of ATP from the cytosolic breakdown of glycogen, or glucose. Does that make sense? And we'll also see that one of the secrets to keeping the ATP coming in the cytosol, if your mitochondria are not yet ready, you must have naked or oxidized state of NAD. Reduced NAD is a product of this pathway, and if you can't get that to go away, you can't keep going with cytosol. And so you'll see that this is one of the key reasons to make lactate, because lactate regenerates NAD. You'll see. What regulates how quickly we break down blood sugar? The energy needs. This is by far the biggest. This is the teleologic or logic of what's happened. That's why you do it. The substrate level regulation has to do with input, so glycogen and glucose uptake are regulated, so substrate feed. Then there we go, phosphofructokinase is your biggest energy step. You're sometimes called rate controlling step with the biggest Gibbs free energy change. So this is allosterically regulated. Oh, so there it is. That's substrate regulation and allosteric regulation of the rate limiting step. So it's pretty classic. I mean, it's a real nice enzyme chain. It makes sense. Here is a set of the environmental regulators on these enzymes. So we just said you get a feedback inhibition from product, but really this has to do more with glycogen. If you have enough glycogen, don't be importing from the blood, or import minimally. Phosphofructokinase, do these all now look really kind of familiar? Stimulator, inorganic phosphate, AMP, the 2 signals of energy deficit that go up the most as a percentage in an active cell, right? I don't actually believe lactate D. If anyone who's better biochemist than me wants to see if lactate dehydrogenase has any sort of an allosteric, I don't think it is. I think it's mostly, it's an equilibrium enzyme that will run either direction based on the balance products. I think someone may have noticed that when there's a lot of ATP, you don't make a lot of lactate, but that's coincidental. It has to do with the energy balance in the cell, not allosterism. Cut. So here's the guts. If you can live through this, you'll live through the lecture. So here's the details. Here we have glucose 1-phosphate. Where did this come from? We have a glucose 1-phosphate. Ah, that came from glycogen. Good. Here is glucose imported by hexokinase. So this has come across the cell membrane and is now trapped in the cell by phosphorylation. Notice that if you have lots of G6P, that will inhibit this. So we have a substrate regulation. Stay off the blood glucose as long as the glycogen is supplying enough. Then we start to move down the classic pathway. Everyone agrees, once you got G6P, your fate is to be broken down into 2 3-carbon molecules. Notice this is a 6-carbon molecule. So you do some stuff that I don't care about. Then you get, I'm a horrible biochemist. You get to phosphofructokinase. And notice that it is a kinase, which means a high energy phosphate is added to this, what has become a 5-ring because you move the 1 carbon up here. So you got a fructose, but you've now managed, because of phosphorylation at entry and phosphorylation. Hey, by the way, I just wanted to make a point. When you break down glycogen, notice what you get is already phosphorylated. You don't have to spend an ATP to import it into the cell. You did spend an ATP, but you spent it when you made the glycogen last night after dinner. So in many ways, this thing is preloaded with an ATP, and it saves you one investment ATP. You start to see why glycogen might be the better choice. for rapid. It's like it's already here. It's already phosphorylated. Let's use that. Okay? Interesting point. Now, when we get to phosphofructokinase, we add a second high-energy phosphate, so now we have a bisphosphated goober. And this immediately, aldolase breaks it into two 3-carbon, 1 high-energy phosphate beasts. Is that okay so far? So we got an investment step that I think yours are still in red, but this morning I changed these into blue. If you're using glucose from the blood, you spend 2 ATPs getting it ready for energy harvest. If you take it from glycogen, you only have 1 investment of ATP. Again, one of the reasons glycogen is a preferred fuel. This okay? Okay. Then the business then starts to happen up here. This glyceraldehyde, blah, blah, blah. This thing, glyceraldehyde, GPB, it uses a NAD. It reduces that NAD, and when that takes it to this, the 1,3, this thing has the highest Gibbs free energy of anything in the chain, I believe. It's up around 20. And so this thing's highly unstable, and it will fall apart. So all the rest of the steps don't need to be regulated. They're just going to go. And you get a cascade. And notice, as this thing falls down its energy state, you get 1 ATP, 2 ATP, and you get this twice because you have 2 of these molecules. So 4 ATP are generated. Does that make sense? Out of an investment, if you use blood glucose of 2, so you get 2 ATP per glucose if you took it from the blood. How many do you get if you use glycogen? 3 ATP. Does that all make sense? Okay. Very good. Notice that if you're running this system very fast, because you're working at a higher rate than your mitochondria have yet adapted to support, there is going to be a using up of cytosolic NAD. You're going to have a more reduced cytosol. As time goes on, high intensity work with not enough mitochondrial support. So that brings us into the last part. Let me see how... that's pretty good. 5 slides. About a little bit about, so here's glucose broken down to pyruvate. NAD was reduced to NADH. Why do you go one way versus the other? Okay? I think the easiest way, and we'll talk about this in a second, but the easiest way is to really think about how many pyruvates can the mitochondria accept. How turned on is the mitochondria. So certainly early in exercise, when the mitochondria doesn't even realize you've started exercising, all the calcium buildup is in the cytosol, all of the ATP deficit is in cytosol, you're going to definitely go this way. A lot. And notice one of the things that does, you can think of 2 reasons why is lactate made. One is, since the last 4 enzymes in the chain are almost all equilibrium enzymes, it is true, if you start to have a buildup of pyruvate, this last energy step through pyruvate kinase is going to slow down if you start to build up a lot of product. So one reason to make lactate is to simply keep that concentration low to get your last ATP, keep it up at a high rate. So just get a concentration difference. You'll see there's some transportation issues that lactate is much more available to leave the cell or get out of the way, to keep its own concentration gradient low. And then from a biochemistry, for you true biochemistry geeks, the most important is if you don't have that cofactor, you can't even finish your investment phase. And so if you're really making a lot of these and using up your NAD, you need a way to reoxidize the NAD to keep the cytosolic energy coming. Right? Ha! Theodore Roosevelt said, I've just had a very strange association. Theodore Roosevelt said, diplomacy is, oh no, it's Talleyrand, the French diplomat, said, diplomacy is mostly about saying, nice doggy, while you look for a big stick. The onset of energy, the cellular diplomacy here, is mostly about making lactate. while you take the time to get your mitochondria speeded up. Sorry, my brain gets funny. So why is lactate generated? Here's one of your best reasons, is to regenerate the oxidized cofactor that is needed upstream. It also drops the concentration of pyruvate to keep the ATP production coming. Someone who knows how to use K equilibriums could probably help me do the Henderson-Hasselbalch on this, or the balance, to see what the actual products versus reactants are. But my impression is this will run to completion, and if you get something like 1,000 times more lactate than pyruvate concentration, it starts to run the other way. So the direction that LDH will run is basically dependent on substrate versus product. It'll run both ways quite happily, depending on the balance of concentrations. Okay. Cofactor recycling, G3P. That's how you say that big enzyme, G3P. So lactate has gotten a bad rap. Most of this information goes back to like 1917, when A.V. Hill received the only Nobel Prize awarded for exercise physiology. And he didn't actually say lactate was bad, but everyone misunderstood what he was saying and went ahead and made a bunch of unwarranted deductions. So I told you our field, it's hard to apply the information. You can't just take one fact and go running away with it. You've got to really... So lactate does not cause muscle fatigue. It is true that work rates that lead to muscle fatigue create a lot of lactate. That's how the story got started, but it's associated, if not causative. Lactate definitely does not cause muscle soreness. I can take 5 different lines of logic and show you 100 different papers. The soreness you get the day after is not related to lactate. Muscle hypoxia is not what is driving lactate production in a human. And those are you're going to run into that. Someday I'm going to die from biting my tongue too hard at the gym as I listen to athletic trainers who didn't get their education at UC Davis telling people these things. And I'm going, I said I want to be rude. So what is the fate of lactate? Remember, lactate is an absolutely fantastic pre-digested energy source. Not a poison. Yummy, yummy milkshake. So here's inside the cell. This path probably happens a lot when you finish exercise. You've been exercising, you've had a buildup of lactate inside the cell, mostly related to the first 2 to 5 minutes of exercise, as you got your mitochondria activated. But that then stays up until you finish the exercise. Well, lactate can enter the mitochondria to be used. There's 2 ways it can do that. In the cytosol, as you stop bringing in more glycolysis and have lots of lactate, this will start to run backward, and pyruvate will enter the mitochondria through pyruvate dehydrogenase. There's also a monocarboxylic transporter protein in the outer wall of the mitochondria, and that will directly import lactate and then do this conversion in here. By the way, this is kind of nice, because notice when you go lactate to pyruvate, you regenerate a reduced coenzyme. And why is it better to have a reduced coenzyme here than here? Yeah, in here, reduced coenzymes are redeemable for ATP. Out here, they just mess up further glycolysis. Everyone's okay so far. This is a big lecture, I promise. Then another thing you can do with lactate is amazingly freely diffusible through the body. For instance, if a woman is breastfeeding and she does a nice hard workout, the lactate that she builds up in her bloodstream will actually wind up in the breast milk. What was her name? Janice, who Dr. Wahlberg did this study. And it turns out babies don't like the tangy taste of lactate. It's got kind of a real sharp taste. And so she could actually show that if you breastfed immediately after a workout, the baby didn't eat as much. The baby would prefer to feed before your workout, and then that makes you lighter anyways. It's just an interesting. So the point is, lactate winds up everywhere. There's also been studies done. You do the extract, and then you take from the animal's eyeballs. The aqueous fluid is full of lactate. So lactate just diffuses through the entire body water. One of the reasons that's useful is if it is entered into the bloodstream or body water, The heart, for instance, loves lactate. I keep dissing Dr. Oz. I like Dr. Oz. He's just not a metabolist. He's a heart surgeon. I guarantee you that when Dr. Oz finishes a heart bypass or a valve replacement, I guarantee you in the recovery room, he hangs lactate in the IV bag. The way I know that is all surgeons do. The mixture is called lactated ringers, and it's basically IV solution with lactate added because the heart will prefer lactate over any other fuel. It's pre-digested goodness. All right, so getting over the idea that it's a poison. Then another thing that we can do, and we'll talk about this, I think, in a future lecture, is remember lactate is a 3-carbon molecule, and here it's being shown freely diffusing out. The liver has a special enzyme set that if you give it 2 3-carbon molecules, like 2 lactates or 2 pyruvates, guess what you can do with these? You can make a hexose. You can make new glucose. And so this is the process called gluconeogenesis. It's peculiar to the liver and the cortex of the kidney. And here we have 2 lactates coming in, and through the gluconeogenetic pathway being converted into glucose. I have to say, this is laborious. It's an anabolic process, and our capacity for it is small. So the place that we do this is late in exercise. You've been exercising for 2 hours, and your blood glucose has gone from 80 to 60, and now you're dipping below 50, and you're starting to forget why you're running or where you're going. That is when gluconeogenesis becomes very common to resupply the blood so the brain can remember the primary activities it's after. Okay? Two more slides. Oh, we have plenty of time. Any questions so far? So inside a muscle, basically one answer to, so where does lactate go after it's made? The answer is everywhere. It goes into the mitochondria of its own cell, if it can. If it can't, it starts to diffuse out and literally goes everywhere. So inside a single muscle, a really common pattern, let's say you're doing high intensity work, you'll see that fast twitch fibers, both of these fibers will be recruited, but fast twitch fibers are just not very mitochondrially oriented. They're not all about oxygen. They don't care. And so they will tend to overproduce lactate relative to their own mitochondrial abilities. Well, what does that lactate do? Do we toss it away as an evil poison? No, it diffuses out of that cell. Guess what cells would really like more lactate? Cells with a very dense mitochondrial content. That's what a slow twitch fiber is. And so you actually get nothing wasted where the breakdown of glycogen, where there's more glycogen in a fast twitch fiber. If it's actually making energy in the cytosol here, what is left over is not tossed away. It's offered to any nearby cell who is capable of using the rest of the energy out of the lactate. Right? So here, this last slide, we saw you can put the lactate in the bloodstream and distant organs can use it. You can also use it inside the same muscle and just share it with a fiber who is not. There's also situations where there may be fibers that aren't yet recruited if it's a moderate workload. And the fibers that are still at rest, they're not actively contracting. It's like, oh look, here's some lactate. This is cool. Someone made a milkshake for me. Is this all okay? Oh, this is good. I think we got one more important slide and we'll quit. One more after this. You can, I will admit that lactate will go up if you create certain interesting situations, like when we put a surgical tourniquet on the limb to do a bloodless operation. We cut off blood flow to the limb for up to 2 hours. You realize how important it is that muscle have this ability. It's like, you don't need no stinking blood flow. At rest, you get 2 hours for the surgery. Lactate will go up in that limb because you took away its oxygen. Realize how rare that is. Paleolithic life, the Neanderthals weren't. During rapid transitions from rest to exercise, this is by far the most common. When does lactate production go way up? At the start of exercise when your mitochondria isn't yet accelerated and yet you need the ATP right now. At high intensity exercise, when you've used up all your primary aerobic tissue and still need more force, you're going to invite the lactate makers to the contraction party. And then if you're at VO2 max, if you're at maximal oxygen consumption in the 5K and you're at the finishing sprint and you suddenly pick up your pace, Where is that picking up coming from if you can't do any more oxidative work? It's coming from anaerobic glycolysis, from cytosolic lactate. So to finish, and I said this already, but it's worth saying a few times, the simplest answer, you can make a lot of answers about what determines where a pyruvate goes. Does it go into, I think I made, let's see, this branch is going into the mitochondria, so you might want to draw a wrinkle bean around this, versus is going to lactate. By far the things that favor lactate formation is the start of exercise, or you're working on the bike ergometer at 50 watts, and your coach turns it up to 100 watts. Coach! You're going to have an increase in lactate until your mitochondria catch up. Anything above VMT, in any condition that increases NADH, if you get really, really drunk, I mean, this is not an experiment, if one is highly drunk, you increase the reduction status in the cytosol, so NADH goes up in the cytosol. You can tell people that are drunk by measuring their lactate. It happily goes up because you flooded the cytosol with NADH. All right? And then you can see these are mostly the real evolutionary pressure here was for it to start to work, you need some energy coverage until the mitochondria speeds up, and then after the work is done, no lactate is wasted. Unless you breastfed it to your baby. I guess the baby's going to use it anyway. No lactate is wasted. It's always reharvested. Okay? And then the last slide is just for you to look over. It's a big summary slide. Very good. If you can